So, let's go ahead. There are different ways of how to work with images, and depending on your background, you can have different ways of looking at the images. And this pie chart here gives you the different ways. To begin with, an image is just more or less a bucket of pixels or voxels. And how you handle it now depends on your background. And first of all, we have the experimentalist who has the background on the experiment itself, usually do a problem-driven top-down approach with a reality model-based approach. Examples could be cell counting, porosity, distribution of concentrations, for example. And then we have the computer vision approach, which is method-driven. The computer vision expert knows a lot of algorithms how to produce a result. So it's feature-based, looking, for example, at edges or some other shapes. It's image model-based, so it's based on features in the image. And they even may engineer new features with the image processing approaches for solving the problem. Then we have the deep learning, or actually more data scientific approach, which is result-driven. You do some experiment and you know what you want to have, and you train some kind of machine to give you the results. So it's biology inspired. Much of the neural network approaches, they are based on what the brain is doing. But in general, machine learning doesn't have to be neural network or deep learning. It's also a lot of regression methods. And in principle, it makes a new take on the image processing and analysis. So in some cases, it's even from scratch. Examples of that could be putting captions on images or identifying unusual events. So it's kind of an exception or anomaly detection. Captioning images, you probably already know. Most of your image categorization tools, also Google, you can even search for something and it gives you a lot of images. And that is done originally by some kind of deep learning approach. And now switching over to a more technical part, and first is the image formation. And typically the image formation process is that you have some kind of excitation, if it's light, X-rays, ultrasounds, microwaves, whatever. You let it pass through some sample, and there is some response caused by this sample, and this response is registered by a detector. All parts depend on which technology you use, but in the end, you will get some kind of image information that represent the sample. A question or just stretching? Good. There is a lot of different imaging modalities, and they have then, of course, also different impulses and what kind of responses they do. I'm not going to read the whole thing. What I'm personally working with is the neutron radiography, tomography, and X-ray based method. And in some cases, also some microscopy, but neutron radiography is my main topic. And the acquisition of images is that you have your original image. This is some kind of tomography slice. But anyway, if you look at it and do a measurement, you may get something like this, bit blurry, maybe flipped upside down because the lenses do things to the image. And also maybe in the camera you forgot to flip it. That one doesn't give you the information you want, so you do some kind of reconstruction. In this case, the reconstruction was a deconvolution, so it takes the task of the deconvolution is to take out the blurring. That is a quite unstable method, so you may get all these ringing effects, but still you can get some kind of better image than before. And the other one is the indirect computational method. So then you do the measurement, for example, in the Fourier space. So you get a lot of frequency information, which is the case for MRI, for example. And then you really have to do some transformation in order to get to the final object. So these are the two typical approaches. One is going directly, and you get more or less what you have is what you get. And the other one, oops, wrong way. And the other one, you always have to take a transform into the observation space. So traditional imaging, you have your light source, which is passing through the object or reflected on the object, and a lens which projects the information on an image plane. And that is microscopy, traditional microscopy, all the radiography techniques, but not tomography. Tomography is actually an indirect method because you need to do this transformation in order to get your data. And putting a little bit more math into it, we have a lot of equations and modifications. So you have, first of all, you have the light source, which may have one produce some kind of beam profile. It's not always that you have a perfect homogeneous light field, but rather some increase of intensity towards the middle. Then you do some kind of sample absorption or reflection. And it could even be that you have some space propagation of the wave going through. And afterwards, you go through some optics, and finally, you have the detector, and each component adds a layer of convolution or something else, multiplication, addition, and that makes the whole information equation of the acquisition quite complicated. And that is only for the monochromatic case. If you would then also add that is polychromatic, then you need to add to this equation, you need to add the lambda for each response function in order to get your image. And yeah, in principle, a color camera has done it in a, say, clustered way. So you have typically the RGB channels, where each channel corresponds to a subspectrum for the red, green, and blue. So it has reduced the spectral information a bit, but there are also cases when you do the full spectrum that can be produced by the source. And indirect computational imaging, you can do, of course, the tomography. You can also do some microlens, diffraction patterns, even topography, so atomic force. Hey, where is my pointer? No, wrong way. So that's the pointer. You can also do atomic force microscopy, where you have cantilever that's following the structure. And in this case, this is a computed depth of focus. So they have done a lot of images, and then afterwards they can reconstruct the depth of focus. So you have the far field and you have the near field, and that can be computational determined. So this focusing is done computationally and not through changing the lens. So finally, we're going to come to the images. And this is more technical side of it. So first of all, very abstract, what is an image? It's in principle a pairing between spatial information and some intensity information. And mostly it's just, or very often it's only a single scalar value, but it can also be tensor valued. So in some cases you can have a full spectrum behind each position. And in most cases, this is 2 or 3 dimensional positions and single scalar. Yeah. And in the real world, everything is continuous. You can go infinitely small, more or less. And to bring it into the computer, we need to do some sampling, actually a lot of sample. And the sampling is bringing it from the continuous space into some kind of discretized space. And there are different kinds of discretization. So looking at the continuous case, you have a smooth curve, you have a smooth gradient in space. But when we do the discretization, first thing is the intensity must be discretized into small stepwise values, and also getting the image itself on a grid. We don't have infinitely small units in the memory, so we have to make it in some kind of grid in order to bring it to the memory. And first of all, looking at the sampling, we can see here we have an original image, and then we can do downsampling by 2 by 2. You don't see much difference, but if we do a downsampling by 32 by 32, you can see that it's getting very blocky and pixely. That may be sufficient for some investigations, and it will save you a lot of space and also computational time. But in some cases, you really need that level of detail that you have in the original image. There can be also approaches where you can start doing an initial categorization on that one to identify this is the one I want, and then you do the heavy analysis on the few that you have selected. Same goes for the gray levels. The original one is 8-bit, so it's 256 gray levels, but you can also reduce the number of levels. With 16 levels, you can actually see the sample pretty well still, but you have reduced the information amount quite a lot. So it is from 8-bit to 4-bit. 4 levels, on the other hand, it's almost too much, but in some cases you can also use that. But 4 levels is more when you already have done some categorization, segmentation or something like that. So you can play with these in order to reduce your data and also reduce the processing time. Then something that is very often confused is the pixel size and resolution. And you often hear that this screen or this camera has a resolution of 20 megapixels. Resolution in that case is not really used in the correct way. Resolution is something that comes from the physics and telling you more or less how smooth the imaging happens thanks to the lens system and also detector system, and can be measured thanks to with the help of modulation transfer functions. The pixel size is the smallest unit that you have within the image, and it also tells you the sample pitch between 2 pixels. If you go really deep on the different detector technologies, it can be that the sample pitch and the pixel area, the active pixel area, is different. But anyway, it's in the computer afterwards, it's represented as the smallest area that is represented. And that's more or less a repeat of what I had before. So it's downsizing the different pixel sizes. And here you can see the effect of different resolutions compared to the pixel size. In this one, you have an ideal edge. It goes from material into void. And then you have a very sharp edge like this. But in reality, when you measure something, you will have this kind of smooth edge which spreads over several pixels. And typically, the sampling theorem states that you should have twice the number of pixels as the highest frequency you have in the image. And otherwise, you will get some ugly effects. So, image intensity. Let's see. No, that was something that should be executed, I see. Let's see what comes. Yeah, okay, there was just the gray levels. Okay. So, how many bits? So I talked already about bits and showed you some effects of it. And the question is how many you need, depending on the task. So few bits, say 4-bit and less, is usually when you have very high contrast data, very clean data, and could also be used for segmented data. Many bits, so going from 8 and even up to 16-bit, is when you have low contrast. Maybe you can only use a fraction to get the level of detail you need. It's also when you have noisy images, it helps to have many bits. And if you want to study gradual changes, so it's not really material and not material, but there is some kind of smooth transition between the levels, then it's also good to have many bits. Floating point is another alternative. So the first two here, they were talking about integer values. And then you can also work with floating point, and that is particular when you have high intensity dynamics. Can also be needed when you do quantification of physical properties. So for example, measuring the water content in the image, or of course in algorithms. Many algorithms do the calculations in floating point. We will see some of them later, not today maybe, but no, we will also see it today. Yeah, but in algorithms mainly you do the calculations in floating point, and then you may switch back to maybe 16-bit or 8-bit afterwards. So when you look at the image, one is just looking at the pixels by themselves, but doesn't tell you very much. So one thing we do a lot to get acquainted with the data is to look at the histogram. And the histogram is the distribution of gray levels, how many gray pixels there are for each gray level. So looking at this histogram, you can see in the image that it starts at intensity 0.4, and then it starts getting some distribution into bumps. So there are two, you can already see here that there are two categories in this area. And then you have a very high peak here, and that is corresponding to the background. So what you're doing is just counting, taking a pixel, looking at the pixel value, and then you put it in the right bin in the histogram. Yes?
The x-axis of the histogram is the intensity?
Yes, yes, or intensity bin. So you have to, unless you have 8-bit images, you usually bin several gray levels together in one bin, because otherwise it will be too detailed. And here I point out some regions of the histogram. So you have down here, you have the low intensity coming to the dark one. Somewhere in the mid-range, you see here on that point. And then you have the high peak of that. And actually here I used the pixel values normalized from 0 to 1. But it can also be whatever. If you have 16-bit, you can also have 0 to 65,000. Depends on what kind of values you have. So it's not really so important exactly which value, but it represents the pixel values. Then some examples. You can have, for example, this case here is a noisy bi-level image. So or actually it's more than bi-level, to be honest. But you have mainly, you have the white background, and you have some black in the main components. And these dots here, they actually have some gray level. And if you look at this histogram, you can see that, of course, the black gives you a very high peak. And then outside, this one gives you the peak for the noise in the white area. And you can see some jitter down here, and that is corresponding to these circles that I have on the arms of the cross. There's not much information in it. And one more thing you can see in the histogram is actually, in particular in this histogram, you can see the statistical distribution, which is Gaussian. And you can actually see that also in the histogram. When it gets more complicated, when you have, for example, a radiograph of something, of a natural object, it's much harder to do a conclusion about the distribution because there is such a mix of different materials and different thicknesses and everything. Another more advanced type of histogram is to look at bivariate data. So for example, if you have two modalities, here I use X-rays and neutrons from a soil sample, then you can see the distribution, the co-location distribution of the two modalities. In medical imaging, it's typical to use X-ray, CT, and MRI, and combine it to have some kind of structural information and functional information. And from there, you can see that some items that were not so easily to identify in each modality, they turn out in this bivariate histogram. You can see even very small distributions, like for here, from the roots, you can see a little bump that you can actually work with later. Gray levels is also a topic how you visualize them. The human eye is capable of seeing about 32 gray levels. You probably can see it also in this image, 32. You can see that it's a little bit banded. 8 levels, no problem. If you go up to 56 gray levels, you can't distinguish anymore where the different levels are. So we have to have some tools to handle this, because as it is images, the visual feedback is relevant, at least for the first assessment. So for the first qualitative assessment of the data, it is good to actually look at the images. Otherwise, you don't really know what you're working with. And what we can do is we can play with the brightness. So we say we only want to look within a narrow interval of gray levels. Then we can focus on regions with these gray levels. And here you can see on the wood piece that with the red one, you can see only these pieces here, but you have a better contrast. You can better see different details than you could in the original image, because you stretch the visible range for a small number of gray levels. If you look at this one, this region here, you can more or less only see the boundary, which may not be so interesting, but just as an example. Then you can also play with the contrast and looking at different bands, like the full width or just a narrow band. So these are tools that you can play with in many image processing tools, like ImageJ is a really popular first go-to. It's an open source tool where you can easily load images, do basic processing, getting acquainted with your data. So it's a good first go-to tool, but I don't like it for mass production. But you can get a first sense of what the images are with the help of that. So, 2D intensity image. Now looking at some Python code. Maybe I should zoom it in a bit. Let's see. Whoops. Yeah. So, what I'm doing here is just producing a random image. And then I create a grid. So I have the X and Y coordinates. This is now placed in a table, and afterwards we can just see the first 5 values of the table, which is an X and Y coordinate and an intensity. This is a quite awkward way to look at an image. I mean, it's 2D, two-dimensional spatial information, but sometimes still it's good to know where you have the X and Y coordinates. But it's much easier to viewing it as an image, and here I actually have so large pixels that you can even plot in the pixel values. Sometimes it's actually useful in your analysis or in your development to be able to plot these the pixel values in different regions. Another relevant part is to have a color bar telling how you associate these different gray levels to values. But gray levels, as you saw, are not so easy to work with, so we can also colorize our images by using color maps. And it can be very beautiful, and some features are even easier to detect. You can, with the help of the choice of color map, actually highlight on different features in the image. And you can, with one color map, you can see more rapid changes, and with another color map, it's easier to spot slow changes in the gradient. So the color map can really be helpful, but it's important also to know that these colors, they are not physical at all, because what you have in the image is essentially only an intensity value. But by putting these colors, you can really spot different features. So you can see here, for example, in this kind of color map, which is kind of monochromatic or bichromatic in a way. You can see that, for example, this outlier is very visible, same as for here. It's very visible. In this rainbow color map, it's not so easy to spot that outlier. So that already shows you the effect of having the color maps. Also, we can look at the pseudo-colors on real images, and you can also see here that here it's easier to spot different levels than it is in this one. But here you can better see the edges. In Python, we use as starting point a library called matplotlib, and it has a lot of color maps, and it's up to you to play with what you like. You can see here there's really a great amount, and if this is not enough, there is also some other more here. Yeah, and if this is not enough and you want to really do crazy stuff, you can even produce your own color map. Mostly it's not needed, but there are some occasions. And the color maps, they're combined, usually are out of 3 color channels. So we have red, blue, and the green. And you can see here, the components are divided into red, green, and blue. And then you can see how the intensity is varying within the different color maps. And typically the color maps is a kind of a lookup table. So if you have intensity 0, it corresponds to, let's say, red. And if you have intensity 255, then it corresponds to blue, just as an example. And there is also some creative things like this grayscale logarithm lookup table. Then actually the gray levels are translated into a logarithmic scaling, and that can give you a quick change in contrast if you look at these two. You could, of course, also just compute the logarithm of the image. That's another way. But the lookup table is probably faster if you want to do fast or rapid coding. The hot map is another one, which is quite popular, actually. And from here, we switch. So now we just looked at the pixels and their values. But the important thing when you do image processing is that you can do actually calculations on the pixel values. And today we're only going into pixel-wise operations. So you can do the arithmetics. You can also apply different nonlinear functions. And then you can do statistical functions. So computing the mean value, the standard deviation, looking for min and max values in the whole image or in regions. So then you just sum up and do things on clusters of pixels. An example is do an image normalization. Typically, as I mentioned before, we have not an homogeneous illumination of the images. So we need to normalize the image, the acquired image, to the reference open beam image or flat field image. So this is a very common operation where we have the image, we subtract some bias which may be caused by the measurement system, and then we divide it by the open beam or flat field, and also that one has a bias that we subtract. And here is an example how that would be done. So first we need to read our images, then we do the normalization calculation, and this is quite straightforward to do in Python, because you can do on these so-called NumPy arrays, you can do the arithmetic in a normal way as you would do it with scalars. If you would do the same thing, for example, in a more traditional language like C++, then you would have to have a couple of loops to go through every pixel and do this calculation and put it back into array. So this is a much easier way of doing it. And then I'm doing all the calculations, and then this part, I usually mark it up, try to mark it up always as visualization. It's for you to look at if you like, or skip. As you can see, it's a lot of more writing than the operation itself. So that's why I try to put it away. And the results, let's see, I think it needs to be executed. Yeah. Why? Oh, I need to zoom down. Yeah, there we have them. Okay. So here I show the different steps. We have the image of the sample. We have the open beam, and as you can see, it's quite inhomogeneous, and there are even stripy things in it. Then with the dark current image, here I visualize that's just black, but it is more or less a bias with some noise on it on the top. And the normalized image is very much flat outside the sample, and the sample itself comes out much clearer. So it's easier to work with for one, and it's also better for the quantification. If you would do tomography, this is the information you need, not this one, because that one would introduce a lot of biases which are not really nice to have in the images. Until now, we looked at two-dimensional images, but it's not uncommon that we have three-dimensional data. And typically, there are two main categories. One is that you actually have a volume, which is three-dimensional, but also movies can be observed as a three-dimensional image when you do the analysis. So it's quite common that you do kind of a volumetric processing on movie data. And there is also a way that you see here, there's a bouncing ball, bouncing with a sine curve, more or less. And if you want to analyze it, you could even do take out a slice in this plane. So you would have a y and time plane, and then you can see nicely how this bouncing ball is bouncing around. And the NumPy array of a three-dimensional image is that you will have actually multiple array that is stacked into each other. So you have, in principle, you have slices, and then you have slice planes, and this is the way how a volume would be, a very small volume would be presented. You can, when you look at the three-dimensional information, do it in different ways. The very simple way is to look at just extract slices and bring them up together. Here is used as a montage of the slices, where you can see slice 1, 2, and 3, and you can see as it was increasing numbers, you can also see on the color level here that it's actually numerically changing. So this is a very basic way. Otherwise, you could also have sub-panels where you show them, but at some point you probably want to do some 3D rendering of it to get a better idea of the data. For the images, that's the big challenge, is when you have time series of volumes. And this is, for example, what's happening when you do observing a process in 3D. Like at the synchrotron beamlines, they often do scans of something that is happening. Could be a bubbling. So you saw actually before this bubble 3D image. That was actually a 4D information. And that introduces quite some challenges, because wrap your head around 4-dimensional when you want to do the analysis ends up probably in that you extract information first in each volume and then look between the volumes or something like that. But I will look into more of time series in lecture 8, I think. And the other thing is you can also have more pixels. Value per pixel. So here we have a table with X and Y values, but there you have some intensity and transparency for each pixel. And then is the question how to present it. So you could, on one side, you can just show the two informations on the side of each other, or you can also look at some kind of hyperspectral information. Then typically what you would probably do is to look at show where you have your measured points and then maybe drill down on each point. So behind each of these points there could be a spectrum of 200 points. And it's a little bit hard to visualize it, but I will also show how to handle that in a later lecture. And here we can look at the pixel value. So you have a wave number and you have the corresponding measurement for that wave number. And this one should be executed. Let's hope it works. No, I didn't. Okay. I think I need to go back a couple. Yep. So this should, no, yeah. So here you can see some examples of some pixels and how the spectrum looks like. It's quite ugly data, I must say. And then the final step, I think, for today is the workflows for image analysis. What we do is, as you have seen, or can assume, one image takes maybe second, fraction of a second, maybe a minute. But when you're working with many images or even volume data, it will take some time. And one thing is that the computers work for us. And one thing that describes what... oops. Hey, come on. Okay. So. Describes the development of CPUs is Moore's law, and that is that the number of transistors doubles every 18 months. And it still does it, but the problem is that the clock speed has slowly reduced or tapered off, landing around 3.5 gigahertz, and they never get faster. So the trick is that they will put more CPUs on the chip, and that has been a story since quite many years now. And if you have many CPUs, you also have to have your code prepared for it. And that means you need to have parallel. Either you have to use parallel libraries, which use the full power of the CPU, or else you have to code it in a way that it's parallel, but that's a bit more tricky. And yeah, and another thing is that has been coming now the last, what should I say, 8 years or so, or yeah, say 10 years, is the GPU. So it's the graphics card that can do computations for you, and they are dedicated processors, and very many of them, and with that you can speed up things radically. You can get really good speed up using the GPU, but that's also special coding. Some cases, again, libraries are prepared that use the GPU. In particular for the machine learning, you can just make some switch and then it's actually working on the GPU. Also, tomographic reconstruction can also be done on the GPU. So if you have a lot of the same computation, it's really useful to to use parallel computations. So parallel processing is really, really important. And there is also, if you don't want to buy a heavy workstation, there are also resources out on the cloud. So there's a lot of these tools. One I'm actually using in the exercises, so you can use the Google Colab. But there are also other things. And the thing is that a heavy workstation for doing image processing may cost, say, 10,000 francs. And that's quite a lot. And usually you're not allowed to buy it on your usual PhD grant within the project. That's something that SNF doesn't like. So it's hard to get the motivation for buying these machines. But on the other hand, you are allowed to budget use of resources. So it doesn't cost very much to buy in and run processing on external resources. And that, I think you can actually get into your budget for the processing. So an example here, a PhD student is about 400 times more expensive per hour than buying in on one of these Amazon EC2 machines. So it's worth thinking about. And there are also many services. And I think we can even apply for time in the Swiss data center in Ticino. That's also an opportunity. But there you have to apply and have some proposal for getting the computing time. So getting back to the basics, workflow analysis. This is cooking, essentially. I like cooking. But anyway, making a simple soup. So first step is you buy some carrots, then you buy meat if you are not vegetarian, then you chop the carrots into pieces, and you should also chop the potatoes, then you boil the water and wait until it boils, and then you add all the veggies and wait 5 minutes, and then you add the meat. So that would be kind of a workflow how to make a simple soup. But probably you can already spot some things that can be done in parallel, and that is the idea of same idea that we aim at in our processing. So what we could do is we could do steps 1 to 4, and then we can mix carrots with potatoes, and then we add some eggs and mix and so on. So you can see that this is a little bit more complicated, and in the end we can write it up like a flowchart like this, where you can see step going by step. And there we got it, the complicated soup. Then you can see now that some things can be done in parallel. So you can buy and chop the vegetables, and at the same time you can put the water on the stove and wait for it to boil. And those things can happen in parallel, and that would be tasks that you can spawn off on doing. So, for example, the parallel would be that you know that it takes time to read images, and that you can interleave with doing some processing, and with that you can speed up your whole workflow. Also, you can make it in steps. So the first image takes a little bit longer time, but then while one is processed, you can read in the next one, and there you have a way to increase the speed of your workflow. Other things is just that you can chop off your image in multiple regions and process them individually if it is separable, and that could also be a possibility. So, and with that we also have DAGs, so it's kind of a structure that is supporting this kind of parallelization, and there is a lot of tools out there listed here, and with them you can also do a lot of parallelization, organizing your workflow, so it's pretty helpful for the parallelization. And of course, when you do go into deep learning, you really want to do it parallel, because it's so many parameters, and so many pieces that needs to be brought together that if you would do it in a sequential way, it will take so long time that you would give it up. But while you would, if you would put it on the graphic card with, say, 1,000 processing units, then things can happen in seconds or minutes. Yeah, and that was it for today. Next week, I'm going to talk about data sets and data augmentation, ground truth. And there will also be an added part about Pandas data frames, which is more coding side. But it's a very useful concept for storing your data and information. Yeah, so I did it pretty well in time this round. Just let's see, where is it? Ah, there it is.